All right, here's one more video on the chi-square goodness of fit test and the follow-up procedure that we would carry out should we reject the null. In this particular example, we're looking to see genes, recessive genes of a particular plant, and they should follow a 1-to-1 ratio based on capital G being the green variety, the lowercase g being the albino, and then we have two of these guys, right? You could get capital G from one parent plant and lowercase g from the others, twice as likely to be yellow-green. So we should end up with 25, 50, 25% ratio of these different types of plants. So to test this, 84 randomly selected pairs of plants. Turns out 23 were green, 50 were yellow-green, and 11 were albino. Do these data differ significantly from what biologists have predicted? And we'll go with the alpha equals 0.05 to answer this. So again, we can either write out in words that the prediction, let's see, the biologists, maybe there's multiple biologists, predicted color distribution for tobacco plant offspring is correct. It is what they say it is. And it's been stated in the problem. I wouldn't worry too much about restating it. If you want, P green is 0.25, P, that's yellow green was 0.5, and then P albino was also 0.25. Versus the alternative that the biologists predicted color distribution isn't correct. At least one of those stated proportions, 1 pi, is incorrect, meaning these guys up here. So we'll again go, this is a chi-square goodness of fit test. There's a distribution that we expect, and we're going to see if the data are different enough from that. Chi-square goodness of fit test, either by name or by formula. And random, large sample size, and independent. Random sample, should have underlined that up here. Test our hypothesis, biologists made randomly selected pairs. There we go. Large sample size, so we have to come up with the expected counts. Given that there were 84, and we expect 25%, 50%, and 25%, this is going to be 21, and that's going to be 42, and therefore the albinos also expect 21, and that should add up to 84. All of those are greater than or equal to 5. And then independence, some comment about inheriting traits is independent. And at least 840 plants in the population, because they were randomly selected. So anytime there's a random selection from a finite population, that's where our 10% rule is going to come from. All that's been established, so we can do the work. So our chi-square equals, and there's only 3 of them, so I'll write all of them, but I would say at minimum, give me the first and last calculations in the sum, but this isn't too much effort. 11 minus 21 squared over 21, and either, again, work that out on your calculator, put it in a list, or run the chi-square goodness of fit test on your calculator if you're able to do that. Degrees of freedom in this problem is 2, because we had 3 categories. And if we go look this up on our table, I've got my calculator in front of me, so the p-value is 0.0392. If you were going to look on the chi-square table for 2 degrees of freedom, this number 6.476 falls between 0.05 and 0.025. So 0.025 p-value and 0.05. So you can just bound it, just like with the t-table. This answer is worth as much credit as that answer from the calculator. Either is fine. Now, our conclusion based on that is the p-value is less than alpha, therefore we reject the null hypothesis. And we have evidence, convincing evidence, that suggests the distribution of plant color is different than the biologists claim. Distribution, something to that effect. Their thing was incorrect. And since we ended up rejecting the null, that means at least one of these, whether it be that was green, this was yellow-green, and albino, that means at least one of those was significantly different. And so what we want to do is find out which one of them is the biggest contributor to this chi-square value. Now, looking at them on the surface, we might be saying to ourselves, okay, well, actually the green one's 23 versus 21. That's not that much different, only off by 2, and we expected 21. So kind of in your mind's eye, thinking it's about a 10% difference. Now, this one is an 8 unit, right, difference. We had 50 versus 42, so we had 50 more than, or excuse me, 8 more than we expected out of 42. And this one was 10. Now, you just want to be careful that just because this is 8 different and this one's 10 different, it doesn't automatically mean that this is the biggest contributor. Because remember, you're squaring the difference and then dividing it by the expected. So yes, this one is absolutely off by more, but the real kicker is that we expected half of what we expected over here. This is off by 10 out of 21. So really, we were 50% short in that particular instance for the albino, where this one was maybe we were 20% over the 8 out of the 42, something like that. So it turns out that this guy right here, the albino, was the biggest contributor to the chi-square statistic, this 6.47 number. This piece alone, the albino calculation, was 4.762. So as soon as I calculate that, I know that the other two only make up the other basically 1.5 that get me to 6.4 there. So the follow-up analysis, when you reject the null in the chi-square, oftentimes you'll be asked for what was the biggest contributor. And so you'll need to either go back and look at your contributions from the calculator, or if you're not using the calculator, go back and look at your calculation and see which one was off, not only most off, but relative to what you expected. And in some of the problems, you'll be asked for that follow-up analysis. And so we're looking for the biggest contributor to that number. So hopefully that makes some sense. Make sure that if you've checked these out and tried the problems, if you run into any issues, that we'll meet and discuss those next time we meet for class. Thanks.